Hello, so let us solve the problem now. This function is given. In the first part, we're supposed to find the domain of this function. The domain of the function means the set of all values that we can use for x, and still the function is sensible. So of course, we know that for this function to make sense, under the square root sign should be a non-negative number. So we demand that 24x minus 8x squared be a non-negative number. Okay? Okay, so that's the quadratic inequality. To solve a quadratic inequality, one way, of course, is to determine the roots of that quadratic polynomial. So I myself equate it with 0, and then I try to solve that. So I factor 8x out. From the first one, 3 is left, and from the second one, x is left. And then the product of two numbers is 0, so this gives me two roots. X is 0 is one of them, or x is 3 is another one. So these are the roots of this second degree polynomial. But you know that the graph of a second degree polynomial is a parabola. And the parabola here either opens up with minimum or opens down with maximum. And of course, in this case, because the coefficient of the quadratic term is negative, we know that this parabola has a maximum and opens downward. On the other hand, the roots of the parabola are 0 and 3. So if you want to have a sketch of the graph of the function, so here 0 is one of the roots, and 3, for example, here is another root. The parabola should open downward and then passes through these points. So this means that this is more or less the same thing that we can imagine. You don't need to be precise here, but I just sketched the graph. So this would be of this type, either higher or lower, but that is not relevant to my problem here. On the other hand, I want to have this quadratic polynomial non-negative. It means that the graph of this function should be above the x-axis in order to have this to be non-negative. So you see that the graph of this, the red part, is above the x-axis. If I choose x somewhere from 0, including 0, to 3, including 3, because I also admit the value equal to 0 itself. So this means that the value of x should be somewhere between 0 and 3. But of course, you are not allowed to write this as the domain, because by definition, the domain is the set consisting of those values. So that either you can write the domain of f is the set consisting of x's in the set of real number, x belonging to R, such that 0 is less than or equal to x, less than or equal to 3. But you already know, hopefully, that there is a notation for writing this, and that is the closed interval from 0 to 3. Okay? So this set is being denoted like this. So this is the first part of the problem, and the domain of my function is actually this closed interval. For the second part, I'm supposed to calculate the derivative. Okay, so that is the difference of two functions. So if I want to differentiate my function, I differentiate the first part minus derivative of the second part. The derivative of x is, of course, 1. For the derivative of this one, we know that square root of x, the derivative of square root of x is actually 1 over 2 square root of x. But we know that now if x is u, here u is an arbitrary function of x. So it will follow the same idea. So it becomes 1 over 2 square root of u, but because of the chain rule, I have to multiply it by an extra factor of u prime. Okay, so that is the formula I want to use for the derivative of the second part, by giving the role of u to this expression. Okay, so therefore, the derivative f, the derivative of x is 1, minus the derivative of square root of u. I will follow this. So it becomes 1 over 2 square root of u, which is 24x minus 8x squared. Yes? And then multiplied by derivative of u. Yes? So and then I will continue. The derivative of this extremely simple. Because I want to simplify, I can see that I can factor a 4 out. 4 is a complete square, so let me just factor a 4 out instead of factoring an 8 out. So this becomes square root of, I factor a 4 out, so this becomes 6x minus 2x squared, and then multiplied by the derivative here, which is 24 minus 16x. Of course, differentiation is finished. You can actually introduce this as your derivative, but I always have the tendency to simplify the expression if possible. So what I do, I would say that minus 1 over, this becomes 2, and then this becomes 4, square root of 6x minus 2x squared. And here, I factor a negative 4 out. If I factor negative 4 out, it becomes 4x, and then it becomes minus 6. And now what happens? This minus sign and that minus sign multiplied becomes positive, and this 4 and that 4 are cancelled. And instead of writing 4x minus 6 here, I can multiply it by 1 and put it as the numerator. So what happens with the derivative finally? So my derivative is actually equal to 1 plus, and then in the numerator I have 4x minus 6. In the denominator I have square root of 6x minus 2x squared. Am I right? Yes. So this is my derivative. Okay, now for the third part of the problem, I am supposed to find the critical points. So what is the definition of the critical points? So I'm following the course book, Calculus, a complete course written by Robert Adams. So in the book, the critical points and singular points are actually defined differently. So the critical points are those points at which the function, the derivative of the function is 0, the first condition. The second condition is that the corresponding x value should be also in the domain of the function. Okay, and in Adams, if I remember correctly, when they say critical points, they somehow only care about the x value. But in principle, when you say critical point, you mean a point including both x and y coordinates. But let us stick to the convention in the course book. So what I need to do, I need to find where f prime is 0. F prime of x is 0. So this means that I need to solve this equation. I need to put this expression equal to 0 and solve it. Okay? So usually I prefer to get rid of fractions. So I multiply everything by this square root. This one becomes this square root, and this square root will cancel that one, so I will be left here. So I multiply everything by this expression. So this becomes a square root of 6x minus 2x squared plus 4x minus 6 equals to 0. So you see, I am now having a root equation actually. And in order to solve the root equation, I have to get rid of the square root sign. So I move them to the other side and square both sides, yes? So what happens, this becomes square root of 6x minus 2x squared. On the right-hand side, this becomes 6 minus 4x. Squaring them, I get rid of a square root sign. But then this totally squared becomes the first one squared, 2 times the first one times the second one, which is 48x And then I have the second one squared, which is 16x squared. Yes? Okay, and then this is a quadratic equation. I'll solve it. So if you don't mind, let me move everything to the other side. So this minus becomes positive 2, and then it is added here. This becomes 18x squared. Then 6x moved there. It becomes minus 54x. And then I have 36 equals to 0. And fortunately, you see that all these three numbers are divisible by 18. So I divide them by 18 to simplify life for ourselves. So this becomes x squared. And then I have minus 3x plus 2 equals to 0. You can use ABC formula or I don't know, PQ formula, but let me factorize it. It is easier. I need two numbers whose sum is minus 3 and the product is 2. So they are minus 1 and minus 2. So when I factorize this gives me this. So this means that either x is equal to 1 or x is equal to 2. But there is a delicate point here. If you remember from your high school studies, whenever you solve a root equation, there is a possibility that you face a false root. So a false root is a root that you can come up with in the solution, but it is not the solution to the original equation. Because what is happening here, if I ask you what are these roots, you will tell me these roots are the roots of this equation. But I was trying to solve this equation. These two equations, of course, algebraically are not the same. And it turns out they are not even equivalent. Because, for example, you know that if x is equal to 2, then definitely you can conclude that x squared is 4, but not the other way around. Because if I give you x squared is 4, there is no guarantee that x is 2. X might be 2 or minus 2. So mathematically speaking, this equation and that equation are not equivalent. So that's why we have to be careful about that. We have to check these roots. I didn't solve this equation. I rather instead solve that equation. So these are the solutions to this equation. This equation is not equivalent with this equation because of the squaring both sides. So it might happen that I have a false root. So I have to check it out. How should I check it out? I will take this one, for example. I can check it here before the squaring process has started. Yes, so I put 1 here, it becomes 6 minus 2, 4, square root of 4 is 2, so the left-hand side is 2. I put 1 here, 6 minus 4 is 2. So yes, now this is acceptable. So this is a critical point. Of course, I have to check, before saying that this is a critical point, I have to check that the point is also in the domain, which is in this case. But let us see, what do I have for x equals to 2? If I put 2 here again, 6 times 2, 12, minus 8 is 4, square root of 4 is again 2. But if I put 2 here, 6 minus 8, it becomes negative 2. And of course, these two are not the same. So it means that this is not this is a false root and not acceptable. Yes? Okay, so I have only one critical point. As I told you that when we say critical point, I always prefer to have x and y coordinates. Okay, anyway, now we want to go to the last part. We want to talk about maximum of f and minimum of f. So there is a theorem in the book that you know that if you have a function which is continuous on a closed interval, it is guaranteed that this function has a maximum and a minimum. So it will attain its maximum value and it attains its minimum value. And where these things can occur, according to the theorem, either at the endpoints or in a local extreme point within the interval. Okay, so the candidate for the local extreme points within the interval is just the critical point, so that's a candidate for a possible maximum or minimum, and the other points are the endpoints 0 and 3. So the algorithm tells me that I have to check these numbers with the value of the functions for these numbers, then of course then it becomes clear. So I have three numbers, 0 and 1, so and then 3. These two are the values of the function at the endpoints, and this is the value of the function and the internal critical point. So if I ask you what f of 0 is, you immediately answer by plugging 0 into the original function. So what you get is 0. If I put 1 there, so this becomes 1 minus the square root of 24 minus 8. This is 16, 4, so this becomes negative 3. And then if I put 3 here, this becomes 3 minus the square root of 3 times 24, 72. 8 times 9, that's also 72, so this becomes 3. So these are the values at the endpoints and at the critical points, and these are the only candidates. So definitely maximum of function is the highest value here, which you see it is 3. When this occurs, when x reaches to the right endpoint, and then minimum of this function is what? Is negative 3, and actually is attained in the internal critical point 1. So this is the maximum, and this is the minimum of this function. Of course, the problem is finished here, but might be that's a good idea if we can just draw the graph and have a better sense of it, okay? Okay, so I put this function in, so it's y equals to x minus, I have a square root here, and then I have 24x minus 8x to the power of 2. Okay, so this is the function that you see, and as it shows, so this is the function. So you see the highest value of this function is achieved at the final endpoint, yes, and the lowest value of the function is achieved here, which corresponds to the internal critical point 1. Okay, so I hope this video was useful. Thank you for watching this video. Until the next video, be safe and goodbye. Thank you.